This is one of the most common questions you will hear when talking about renewable energy. What happens when the wind doesn't blow and the sun doesn't shine? And it is actually a phenomenal question. At first glance, it feels like it exposes a fatal flaw in the entire energy transition. After all, if renewable energy depends on the weather, and the weather is unpredictable, doesn't that make the whole idea fundamentally unreliable? The interesting thing is that this question is both brilliant and misleading at the same time. Brilliant because it points to a real engineering problem. Misleading because it hides several assumptions that most people never noticed. And once you see those assumptions, you start looking at the entire debate very differently. So today I want to do three things. First, I will answer the question from an engineering perspective and show you how modern power grids already deal with periods of low wind and solar generation. Then I will explain why this question is such a powerful rhetorical device and the psychological traps that make it so persuasive. And finally, I want to look at some of the real challenges that still stand in the way of a fully decarbonized grid. So let's start with the engineering. How do we actually build a system that relies on the unpredictability of the weather? We don't just cross our fingers and hope. We have in place a multi-layer defense system using four main strategies: diversification, overbuilding, storage, and demand response. So let's talk about this. Strategy number one is diversification. But first I need to clear up a common misconception here.
Those windmills, wah, wah, wah. Darling, I want to watch television tonight and there's no damn wind. What do I do?
When people ask what if the wind stops, they are imagining a grid that is totally passive and reactive to the weather. This is not how it works. The power coming into your house right now is not decided by the weather. It is decided by an engineering system based on a highly complex real-time financial market. While details vary from country to country, I will talk of the United Kingdom as an example to illustrate the general principles. Here, a government-owned engineering corporation, called the National Energy System Operator, NESO for short, balances the supply and demand. NESO does not wait for the weather. They use highly accurate forecasts to anticipate supply and demand, while generators and suppliers trade electricity through wholesale markets. NESO then steps in to balance the system in real time. Now, NESO divides the day in 30-minute windows called settlement periods. The most important moment happens about 1 hour before each settlement period. This is a critical moment called the gate closure. Every generator and market participants in the country, like EDF, SSE, or DRAX, has to submit two things to NESO. First, their final physical notification, declaring how many megawatts they plan to put onto the grid. Second, their offers and bids, which are the prices they will charge to turn their power up or pay to turn their power down. Once the gate closes, the menu is locked. At this point, NESO enters the balancing mechanism. They look at the total declared power, compare it to their demand forecast, and say, okay, we have a gap, we need an extra 500 megawatts. Because prices and capacity are already declared, NESO doesn't have to go searching for power. They simply look at the menu and immediately mix and match those pre-submitted bids to build the perfect portfolio for that 30-minute window. But how do they decide who to buy from? NESO buys power based on three main criteria. First of all, cost. They are legally required to find the cheapest possible mix to keep your energy bills low. Now, while minimizing cost is the objective, there are also some important constraints to respect. The first are network constraints. Let's say that there is a lot of wind off the coast of Scotland, and Scottish wind farms are offering incredibly cheap power. NESO may actually reject it, because the physical transmission cables running from Scotland down to London may be already full. In that scenario, NESO may pay a Scottish wind farm to turn off and pay a different plant closer to London to turn on. The second important constraint is grid stability. In very simple terms, NESO needs to buy power to maintain the grid working at 50 Hz and avoid blackouts. So when the wind drops, NESO doesn't panic. They just buy a different product in the balancing mechanism. They may buy power from a battery facility run by Harmony Energy, or they may import hydroelectric power from Norway through an undersea interconnector cable. The point is that the energy mix changes dynamically, minute by minute, completely invisible to you. And it is a conscious engineering decision, not a passive reaction to the weather. Now, if we look at the current mix of energy as of today in 2026, you can see that a sizable chunk of that flexible power still comes from fossil fuels. Specifically in the UK, these are from natural gas plants. Gas is very easy to dispatch, and when NESO needs power fast, gas companies like Uniper or SSE are often the ones winning those bids. So we are currently using fossil fuels to balance the unpredictability of renewables. How do we get rid of them? To get gas out of the balancing mechanism entirely, we cannot just rely on diversification. This brings us to the second strategy, overbuilding. This concept can feel counterintuitive, but it makes perfect engineering sense and financial sense once you understand the difference between how fossil fuel and renewables economics actually work. For the last century, our energy systems were based on operating expenditure, or OPEX. When you run a natural gas plant, the physical building is only part of the cost. The massive ongoing expense is buying the gas to burn every single day. Because that fuel costs money, you never generate more electricity than you absolutely need. Renewable energy, however, follows a different economics. It operates almost entirely on capital expenditure, or CAPEX. The fuel, the sunlight and the wind, is completely free. So the ongoing OPEX is negligible. The primary cost is buying and installing the hardware upfront. And right now, the cost of manufacturing solar panels has plummeted to the point where the panels themselves are one of the cheapest components of a power plant. They are significantly cheaper than the grid connection infrastructure or the inverters required to turn the direct current DC from the panels into the alternating current AC used by the grid. Because the panel hardware is so cheap, it is economically optimal to install a much larger total capacity of solar panels than the inverter is actually rated to output. We can measure this using the DC to AC ratio. In the past, you may have matched 10 megawatts of panels to a 10 megawatts inverter, a 1.0 ratio. Today, utility-scale solar farms globally are typically oversized. Standard commercial projects now operate with a DC to AC ratio of 1.2 to 1.4, meaning that the system is oversized by 20% to 40%. And according to industry leaders like SMA Solar Technology, this trend is pushing even higher, with some system economics showing that maximum profitability is at oversizing ratio up to 170%. So even if the sun doesn't always shine, by oversizing the solar farm, the inverter operates closer to its rated output for a larger fraction of the year. These two strategies significantly shrink the gap in generation. Yet, diversification and overbuilding alone are not enough, because they only act on the moment. We need the ability to shift power through time, and that requires strategy number 3, storage. When you hear storage, your mind probably jumps to batteries. But true grid-scale storage is a diversified, multi-layered portfolio. Let's start with a heavy hitter, pumped hydroelectric storage. We can use excess renewable energy during the day to pump millions of gallons of water up into a high-elevation reservoir. When the wind drops, we open a valve and the water flows back down through turbines to generate power. In the UK, we have 4 major pumped hydro facilities currently operating. Originally built to help stabilize the grid, they are now used also to support renewables. The biggest one is the Dinorwig power station in Wales, which is built inside a hollowed-out slate mountain. Dinorwig alone can supply 1.7 gigawatts of power and holds a storage capacity of roughly 9.1 gigawatts hours. This means that it can discharge at maximum power for over 5 hours. These facilities help to balance renewable unpredictability when the weather is uncooperative. And while we had only 4 facilities in the UK for over 40 years, we are now approving more than 11 new facilities to more than double our pumped hydro capacity. And engineers are expanding beyond water storage. by reinventing decades-old technologies such as compressed air energy storage. Instead of pumping water up to a mountain, you pumped heavily compressed air into a massive underground cavern. For decades, this technology remained relatively niche, but several large new projects are now demonstrating renewed interest in this approach. In January 2026, China officially put the world's largest compressed air plant online in Jiangsu province. It has a capacity of 600 megawatts and 2.4 gigawatt hours of storage, entirely without burning fuel. And now finally, let's talk about the grid-scale batteries, because the technology and its deployment have undergone a radical transformation in just the last 2 years. Historically, meaning just 3 or 4 years ago, grid batteries were relatively small and built for a very specific task: frequency response. What is that? If a power plant suddenly went offline because of a fault, the grid's frequency will drop. Batteries can automatically detect frequency deviation and inject power within seconds to stabilize the grid. So batteries were used as emergency shock absorbers, not for long-term storage. Because of this, critics often correctly pointed out that batteries could not bake up a windless evening. But that is no longer true. The technology has fundamentally shifted from frequency response to energy shifting, which is the large storage of renewable power to balance the grid over multiple hours. According to the International Energy Agency's May 2026 data, the share of new batteries projects dedicated to bulk energy shifting increased from 40% in 2015 to over 90% by 2025. We are now building massive battery facilities designed specifically to capture overproduced wind and solar and discharge it during peak evening hours. In the UK, which now has around 6.9 gigawatts of operational battery capacity, major developers like RWE are breaking new ground on projects like the Pembroke Battery Storage Facility in South Wales. And in California, batteries are now regularly supplying a substantial share of evening peak demand, demonstrating that grid batteries have evolved far beyond their original frequency response role. This brings us to the static versus dynamic psychological fallacy. When skeptics argue that we do not have enough storage to run a 100% renewable grid, they're right about that today. But they're making a static assumption. They fail to realize that this transition is highly dynamic, and storage is being ramped up together with generation. Now, even with pumped hydro, compressed air, and batteries, building enough physical large-scale storage to power every single home and factory during a multi-day winter lack of wind may become difficult. To solve also this scenario, we cannot just think about the generation side, but we also need to rethink how we consume power, which brings us to the strategy number 4, demand response. Instead of just building more supply, engineers are fundamentally altering the demand side of the equation. For the last century, the cardinal rule of power generation was static. Supply must follow demand. When millions of households turn on their oven at 6 p.m., a gas or coal plant has to instantly meet that exact spike in load. But with the deployment of smart grid technology, we are reversing this paradigm. Demand can now autonomously follow supply. To be absolutely clear, this does not mean that a utility company will remotely shut off your Wi-Fi. Demand response targets flexible, invisible loads. That is power consumption where the specific timing of the electricity draw does not negatively impact the end user. And this is already an active, highly effective market mechanism. For instance, in the UK, we have the Demand Flexibility Service, operated by NESO. During recent winters, rather than using expensive gas plants during peak evening hours, NESO paid energy suppliers to incentivize customers to shift their usage. An example of this is Octopus Energy Group, one of the largest UK electricity suppliers, which uses this mechanism through their saving sessions. Essentially, by running our washing machine at a specific time, you will pay less. Just sending notification to customers with smart meters, Octopus successfully shifted 1.86 gigawatt hours of demand and achieved a peak power reduction of 188 megawatts. To put that in perspective, they effectively replaced the output of a small-sized gas plant simply by financially rewarding people to run their washing machines or dishwasher at a different time of the day. But the true massive potential of demand response lies in automation, and specifically in electric vehicles, EVs. An EV is essentially a grid battery on wheels. As EV adoption accelerates, with over 1 million plug-in vehicles already on UK roads and global sales climbing rapidly, they represent a new distributed energy resource. When you plug in an EV at 6 p.m. after work, you rarely need it to charge instantly. You simply need the battery full by 7 a.m. the next day. Through smart tariffs like Octopus Energy's Intelligent Octopus Go, the supplier's algorithm interfaces directly with the vehicle charging system. It can pause the charge during the high-stress, high-price evening peak. Later in the night, when system demand drops and offshore wind generation is high, driving wholesale electricity prices down, the algorithm automatically initiates charging using cheap green power. By simply shifting the timing of EV charging, we absorb excess renewable generation without needing to build large standalone grid batteries. The projected scale of this flexibility is enormous. According to the International Energy Agency, to hit global net zero targets, the world will require 500 gigawatts of demand response capacity by 2030, with roughly 50 gigawatts of that coming strictly from electric vehicles. By treating EVs, commercial heating and air conditioning systems, and cold storage warehouses as a massive automated buffer, we drastically reduce the peak capacity requirements of the grid. We transition from a fragile system that reacts to the weather to a smart system that dynamically interacts with it. So from an engineering perspective, the unpredictability of the weather is a manageable problem. We have the analytical tools, the generation hardware, and the active market mechanisms to deal with this. So if the engineering is well understood, if we have the interconnectors, the overbuilt generation, the multi-gigawatts batteries, and the smart grid technology, why these questions still dominate the conversation? Why does "what if the wind doesn't blow" still feel like a mic drop moment? First, I want to be very clear. If your uncle at a barbecue or a friend in a WhatsApp group asks this question, they're not doing anything wrong. It is a completely legitimate, intuitive question. For an everyday person, it is genuine common sense. But when this question is deployed on a political stage, the context shifts. Now, sometimes this is asked in good faith. There are absolutely real, complex debates to be had about the economics of long-duration storage, the feasibility of transmission upgrades, and how we manage deep winter gaps. But very often, the question is used as a calculated rhetorical device.
The wind doesn't blow. Those big windmills are so pathetic and so bad. Darling, I want to watch television tonight and there's no damn wind. What do I do? I want to watch the election results. Darling, there's no wind. The damn wind just isn't blowing like it used to because of global warming, I think.
Instead of opening a technical discussion about how we solve those specific bottlenecks, it is used as a weapon to imply that a renewable grid is fundamentally impossible. When used in this way, the speaker is not looking for an answer. And it works so perfectly because it exploits several fallacies in human psychology and logic. I think it's important to be aware of these fallacies, so let me run through them. First, the true rhetorical power of this question is that it takes a physical reality and uses it to smuggle in an incorrect assumption. The premise, the weather is unpredictable, is undeniable, 100% correct fact. But the question is designed to make you jump to a false conclusion. Therefore, we cannot rely on renewables and must keep using fossil fuels. In logic, this is a false dilemma. By mixing an obvious reality with a false implication, the person asking the question sounds incredibly reasonable, while subtly trapping you into accepting their underlying agenda. The second trap is simplicity. The question is incredibly simple. A child can understand it. But what about providing an answer? As I just demonstrated to you, the answer is known, but it is complex, and it takes 20 minutes to explain at a superficial level. This creates a massive power imbalance in everyday conversation. This phenomenon actually has a formal name, Brandolini's law. It states that the amount of energy needed to refute a misleading claim is an order of magnitude larger than the energy needed to produce it. When you face this question at a pub, you simply don't have the time or the capacity required to answer it, which makes the person asking the question look like they just won the debate. Now, the third trick is that this question also forces us into a straw man argument. A straw man is a dishonest debating tactic where someone oversimplifies an opposing view to make it very easy to defeat. It is like fighting a scarecrow instead of a real opponent. When you hear wind power, your brain immediately builds a tiny mental straw man.
Darling, I want to watch television tonight and there's no damn wind. What do I do?
You picture a single wind turbine plugged directly into your television. In that scenario, yes, if the wind stops, your TV shuts off. But as you now know, that is not how a national grid works. The question forces you to imagine a fragile, isolated system that doesn't actually exist. The fourth and final psychological trap relies on a complete failure of human intuition when it comes to probability. Humans are terrible at understanding probability without formal training. If I ask you to guess the outcome of flipping a single coin, this is entirely unpredictable. But this does not mean that we cannot say anything about this. If you flip 10 million coins, the uncertainty vanishes. It is a mathematical certainty dictated by the law of large numbers that you will get incredibly close to a 50-50 split. The energy grid behaves a bit like a giant coin flipping machine. One wind turbine is unpredictable, but aggregating thousands of turbines and millions of panels across countries substantially reduces short-term volatility. So next time a friend asks these questions, try to explain what you have learned today. But if it is a politician on television asking this question, recognize what is actually happening. They may be using a rhetorical device that shuts down discussion before the engineering solutions can even be considered. By the way, if you are enjoying this video, leaving a comment below is one of the best ways to support it. Now, as promised, let's talk briefly about some real open problems around weather unpredictability. Right now, as explained in the previous video, renewable energy is riding rapidly along the S-curve. The transition from our current grid to about 70% clean energy is actually rather simple. But eventually, we're going to hit the top of that curve. The last 30%, achieving absolute net zero, completely removing fossil fuels 365 days a year, is going to be much harder. If we want to have a real adult conversation about these difficulties, we shouldn't debate what happens to our TV if the wind stops. We should look at the actual bottlenecks. The first major problem is fundamentally economic. Our free market electricity grids were not built for the weather. This manifests in two conflicting ways. First, who pays for the unpredictability? Right now, the cost of keeping massive batteries and backup gas plants on standby is largely socialized through our energy bills. Some economists argue that we must shift this risk directly to the developers, requiring them to guarantee a 24/7 output. The market is already moving this way. If a wind farm misses its promised target at that 1-hour gate closure, they are hit with financial penalties called imbalance charges. But pushing financial risk onto developers accelerates the second issue, the cannibalization effect. Because we overbuild renewables, a perfectly clear summer day means that every panel across Europe may pump out the maximum power simultaneously. Supply then vastly outpaces demand, and wholesale prices don't just hit zero, they go negative. Europe, for instance, experiences hundreds of hours every year of negative electricity prices because of this reason. Cheap electricity sounds amazing for consumers, but it's terrible for a pension fund investing 500 million in a new wind farm. The very success of renewables is destroying their own profit margins. To fix both of these issues, we may have to fundamentally redesign how market values power. For instance, by moving towards capacity markets, where companies are paid simply for the capability to provide power on demand with long-term price guarantees. But rewriting the financial system of the global energy market without accidentally crashing the economy is a difficult problem to solve. Now, the second problem that I want to mention is physical rather than economic. It is called inertia and transmission infrastructure, both of which would deserve a dedicated video on their own. Traditional gas and nuclear plants use massive heavy rotors spinning at thousands of rotations per minute. That spinning mass provides grid inertia. If something goes wrong on the grid, the massive physical momentum of those spinning metal rotors acts like a damper, keeping the system frequency from crashing. Solar panels and wind turbines do not naturally provide this because they are connected via devices called inverters that can stop almost instantaneously. As we replace spinning rotors with inverters, the grid loses its physical dampers. We have to invent completely new technologies to provide artificial inertia to keep the grid stable. And finally, we have the geographical bottleneck. The windiest and sunniest places are rarely where the cities are. We need thousands of miles of new highly voltage transmission lines, and permitting them can take several years due to local council disputes and not in my backyard mentality. Whether a future grid reaches 90%, 95% or 100% renewable generation remains an active debate among experts. What is clear is that evaluating the future using only today's infrastructure is misleading. The futurist and inventors Arthur C. Clarke once said, "When a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong." Critics are looking at the geography and technology of 2026 and assume that it will remain static as we approach 2040. But this transition is widely dynamic. We're not just building more solar panels, we are also rewiring the entire physics of the network at the same time. The fact that the grid geography we have today cannot support the generation we will have tomorrow is not a failure, it is just an engineering roadmap. Now, these are massive generation-defining complex problems. We have to rewire the physical grid, invent new ways to maintain inertia, and redesign global economics all at the same time. But these are logistical problems. They are economic problems. They are not infeasible physics problems. To quote again Arthur C. Clarke, "The only way of discovering the limits of the possible is to venture a little way past them into the impossible." Thanks for watching, and I'll see you next time.